So as with most nucleophiles, when it comes to the reactions with aldehydes and ketones, if the carbonyl is conjugated, as this ketone is here, then anytime we add a nucleophile, we have to concern ourselves with the idea of 1,2 versus 1,4 addition. Now, the key to that distinction, whether we get the 1,2 product seen here or the 1,4 product pictured here, is all dependent on the nucleophile. And so we always have to ask the question, is the nucleophile able to be a leaving group? And if we can answer yes to that question, then 1,4 is going to be favored. And if the answer to that question is no, then in general, the answer will be we get 1,2 addition. And so this is why nucleophiles such as water and alcohols and amines often prefer 1,4, and things like Grignard's carbon-based nucleophiles, as well as hydride nucleophiles, prefer to give 1,2. So the reaction we have pictured here will give us the 1,4 product. Now that's not to say the 1,2 product doesn't form. The 1,2 product in almost every case is what we call the kinetic product. It forms faster. But if the 1,2 addition is reversible, and that reversibility is based on whether the nucleophile can be a leaving group, then the 1,4 product is more stable, and that will be the major product. So when we draw mechanisms of this 1,4 addition, we won't show the reversible 1,2 piece because we're just presuming that that's happened and it's reversed. And if you want to review that mechanism, there is a video specifically devoted to the 1,2 addition of water. Now, this 1,4 addition can take place either under acidic or basic conditions, same as with the 1,2 addition. Under acidic conditions, we start with the protonation of the carbonyl, and then the water will attack at the alkene carbon, and we shift the pi electrons through the conjugation up onto oxygen. The oxygen adds its lone pair back in. These pi electrons pick up a proton from the acid, and then upon deprotonation of both cations, we get our product. Under basic conditions, we have a similar mechanism, but instead, because the stronger nucleophile is present, that can attack first without protonation of the carbonyl. And then the resulting enolate, or this double bond attached to an O-, adds its electrons back in, picks up a proton from water, and we arrive at the same product. An example of where we might run into one of these 1,4 additions of water is in the following. This is cis-aconitate, and the addition of water ends up being a 1,4 addition. And as a result, we can form isocitrate. And this, in fact, is one of the steps within the citric acid cycle.